to construct the bending moment diagrams for frames. Generally, we solve support reactions firstly. Then, divide the frame into single bars and calculate the bending moments of member and sections. Look at an example. Calculate the bending moments of section 1 and 2 and construct the bending moment diagram for this time. We discussed the calculation of support reactions. For this three-hinged frame, we have solved the four support reactions: Fxa, Fya, Fxb, and Fyb, according to equilibrium equations. According to sigma Ma is equal to 0, we could solve Fyb is half Fp upward. According to sigma Fy is equal to 0, we could solve Fya, that's negative half Fp downward. If we take Cp part as a free body to establish sigma Mc is equal to 0, then we could solve Fxb is a quarter of Fp to the left side. Then, according to the sigma Fx is equal to 0 for the whole structure, we could solve Fxa, that's negative 3/4 Fp to the left side. Then, cut section 2 and take Eb as a free body to solve the bending moment of section 2. This is the free body diagram. According to sigma Me is equal to 0, we could solve Meb is equal to a quarter of Fpl negative. That means the direction of Meb is opposite to what we supposed here. So the right side of section E is in tension. How to solve the bending moment of section 1? We could cut section 1 and take Eb part as a free body. This is a free body diagram. The internal forces of section 1 can be represented by Fnec, Fqec, and Mec. According to sigma Me is equal to 0, we could solve that Mec is equal to negative a quarter of Fpl. That means the real direction of Mec is anti-clockwise, so upper side of section E is in tension. Actually, we could also take joint E as a free body, like this. To calculate bending moment of section 1, if we have already known section 2's bending moment Meb. According to sigma Me is equal to 0, Mec is equal to Meb, both outside in tension. For a rigid joint connecting two members, two bending moments of the member ends are equal and in opposite direction. Then, let's construct the bending moment diagram for this three-hinged frame. According to what we have calculated just now, we have already known Meb and Mec. For the Eb member, there's no external load acting on it. So the bending moment diagram must be a diagonal line. Mbe is equal to 0. Meb is equal to a quarter of Fpl, right side in tension. Then according to equilibrium equation of sigma Me is equal to 0, for the rigid joint E, we know that Mec is also equal to a quarter of Fpl upper side in tension. For the DCE part, Q is equal to 0. So that means the bending moment diagram must be a diagonal line. Section CM must be equal to 0. So we could connect these two sections M by a straight line, then elongate it to section D. According to the relationship of these two triangles, we'll know that MDC must be equal to 1/4 of FPL. Then for the joint D, according to equilibrium condition, MDC is equal to MDA, both inner side in tension. Then we'll know MDA is equal to 1/4 of FPL, right side in tension. MAD is equal to 0. So we could connect these two sections M by such a dashed line. For AD part, there is a concentrated load FP acting on it. So we could take this dashed line as a baseline, superimpose such a polyline. Here this value is 1/4 of FPL. Then we obtained the bending moment diagrams for each part. Example 2. Calculate the frame and construct the bending moment diagram. Firstly, let's solve support reactions. According to sigma Fx is equal to 0, we could solve Fxa is equal to 80 kN to the left side. According to sigma Ma is equal to 0, we could solve Vd, that's upward, 60. According to sigma Fy is equal to 0, we could solve Va, that's 20, downward. Then let's calculate the bending moment of member ends. Take AB member as a free body. This is the free body diagram. For section B, there are 3 internal forces, FNBA, FQBA, and MBA. In order to solve MBA, we could establish sigma MB is equal to 0. Then we could solve MBA, that's 160. According to the direction of MBA, we know that for the member BA at end B, right side in tension. Then let's take rigid joint B as a free body. According to the equilibrium condition of the rigid joint B, MBD must be equal to MBA, both inner side in tension. So MBD is equal to 160, lower side in tension. Then according to the bending moment of member ends, we could construct the bending moment diagram for the structure. According to MBA is equal to 160, right side in tension, we could draw such a dashed line. Then superimpose a parabola because AB member is under the action of uniformly distributed load. In the middle section of member AB here, this value is equal to QL squared over 8, that's 40. According to MBD is equal to 160 lower side in tension, MDB is equal to 0. We could connect these two sections by such a dashed line and superimpose such a polyline due to the action of the concentrated load, Fp. Here for the section C, this part, its value is 1/4 of FPL, that's 40. When constructed the bending moment diagram, we could use the superposition method, segment by segment. That's all for today. Thank you for your attention.